Let us talk about binary search tree, BST. In this discussion, we want to build up a search tree using the concept of binary tree. And binary search tree is very important data structure and very efficient structure to search numbers in tree. In this discussion, we want to talk about few points. What is a binary search tree? Why binary search trees? Binary search tree implementation. We want to see operation, insertion operation in a BST, deletion operation from a BST. We take a look at tree sort and BST as priority queue. Now, the first thing happens is we have a question on binary search tree definition. A binary search tree is a binary tree that is either empty or that satisfies the following property, we sometimes call BST ordering property. In binary search tree, the key of each node, we are talking about the value that is stored in a node, key of each node is greater than each key in the left subtree. That means the value at the node is greater than the value at the left, any left, and the key at each node is less than the key in the right subtree. That means value at the node is less than the value at the right. So each key in BST is unique. An example, you can see that C2 is less than C, but note this iterative construction, you can see to all the left they are less than 6 and all the right they are actually greater than 6. So this binary search tree is a search tree. When you are looking at these numbers, when you do in-order traversal of a binary search tree, it's automatically the number is sorted. So you can see key of the left subtree is less than the key of x, and key of x is less than key of right subtree. So the property of a binary search tree is that the value at the node is always less than the value at the right and always greater than the value at the left. Alright, so let's proceed to have a definition. A most common misunderstanding is that the BST ordering property is only between parents and children, but the key at each node is greater than the key at the left of that node, if any, and right. So you take a look at this example here. What we understand that the left are all less than. So the above definitely not BST. Why? Because even the left we have 22, 25, they are actually greater than 20. So it doesn't really satisfy the property of binary search tree. But the question is why BST? BST provides a good logarithmic time performance in the best and average case. Average case complexity of using linear data structure compared to BSTs. BST provides much better than sorted array, unsorted array and other types of data structure for searching numbers. So binary search tree are an important data structure for dynamic sets and dictionaries. Each element in association object having a comparable value, we can search at a very lowest possible time. When we implement binary search tree, we just need to keep in mind the values, and I'm going to talk from C language point of view. This is the implementation of the find. We'll talk about it in C programming. We can skip this part. Also that searching and how do we do that in case of find mean and find max. But binary search implementation, find successor, also we'll talk from our C language point of view. This is actually Java, so binary search implementation from predecessor point of view. What happens in case of insertion? When we insert, we are actually comparing value at each node. We come to the root first, take a look, insertion. 5 is going to be inserted in this tree. Forget about this code because we will be talking from C. 5 is going to be inserted, so 5 is compared with 6. If 5 is actually less than 6, so it's come to the left. Now next immediate is 2. Is 5 is greater than 2? So go to the right. And then 4 is here already. So it says is 5 is greater than 4? Yes. So go to the right and that's actually inserted. So you are continuously comparing value with the left or the right and you make your position in a tree. Deletion of a tree, the node to be deleted must be, there are 3 cases. One is you can delete a leaf node, very easy. The node to be deleted has one non-empty child. If it happens that there is a non-empty child and you have to delete that node, the node to be deleted has two non-empty children. Maybe a node is connected with two other children and you have to delete that particular node. So what happens here? Case 1, how do you delete a leaf node? You can see it's very easy. When you come into leaf node, you want to delete, remember one thing, you need to delete 5. So you are talking about deleting 5 is just traveling and find out 5 and remove it, because it is a leaf node. You see on the left you have 5, but on the right you don't have 5 because 5 is deleted. So it's very, very straightforward because it is a leaf node. Case 2, if you want to delete a one child node. So if you want to delete a one child node, the first thing is you first come to the value. What is that value? You want to delete a particular target is 5, but 5 has actually, that's the target is you understand the target is 10. You have to delete 10. But so what happens in this case of deletion? You have detected that you have a children 5, so you keep that 5 in a temp, and then reassign the root node to the temp so that it's a single child. It's very easy, but you need to do a reallocation of a pointer to delete the node. So you are connecting a temp to a target, and then whatever target, now you reallocate first and then delete. So that way we can actually delete one child node. But if you want to delete two child node, is very, very challenging because you have a target. For example, if you have a target is 8, you have a two child node. In that case, you really have to reallocate again pointer. You can understand you have to reallocate left and right pointer and then delete. So deletion, well, case 3, deleting a node that has two non-empty children. First copying method, copy the minimum key on the right, because you sometimes have to rechange the value, copying the minimum key to the right and then you delete it. Deleting a node that has actually two non-empty children, method 2, copy the maximum key to the left side, because the maximum always goes to the right and the minimum comes to the left. So that kind of readjustment we can always do. So deleting copying method implementation, these are actually respective codes, but tree sort is coming. Now any of the following in order traversal behavior of BST is actually the numbers are sorted. So the in order traversal of BST visit the node of the tree is increasing sort order, and the reverse in order traversal is the decreasing sort order. That means you are talking about ascending sort. That means sorting the numbers in from a small to the large, or reverse in order means from the large to the small. So tree sort implementation will be talking in the C language point of view, and I can skip this. BST as a priority queue using insert and withdraw max. I will just also have to have some understanding later. So we stop here, and we basically stop here, and we stop here, and we go back to our next discussion once it comes.